Hi everyone, myself and Arun Kumar from SNS College of Technology. In this video, I am going to share about steady state errors. So the following parameters we are going to discuss about this PPT. First one is steady state error, classification of control systems, steady state error of unity feedback systems, static error constants, static position error constants, static velocity error constants, static acceleration error constants, and assessments. So the static error mainly caused based on the number of signals has been generated based on the input signals. If the output of the control system at a steady state does not exactly match with the input, the system is said to have a steady state error. Any physical control system inherently suffers the steady state error in response to certain type of inputs. A system may have no steady state error to a step input, but the same system may exhibit non-zero steady state error to a ramp input. So mainly it can be causes based on step input, ramp input, parabolic input, and so on. So the magnitude of the steady state errors due to these individual inputs are indicative of the goodness of the systems. So normally the steady state error system has been represented by g of s because the g of s is a transfer function of the particular component or control system. So based on the transfer function, we can able to implement the output of the corresponding system. So here they are going to calculate the steady state error for a control system is g of s equal to k into t as plus 1 tvs plus 1 and tms plus 1. So like this they are able to calculate the control system their classification. Here the power n indicate about the representation of the signal type 0, type 1, type 2, like this. So based on this we are able to check the continuity of the signal as well as the constant of the signals. Here, as the type of number is increased, accuracy also improved. However, increasing the type number aggregative the stability problems. A compromise between steady state accuracy and reliable stability is always necessary. So let us consider the system. The error has been generated based on the input signal and overloop of the system. So the error system E of s is calculated based on the transfer function of the system. So the system is calculated by C of s output by input R of s equal to C of s plus g of s divided by 1 plus g of s. So here 1 plus g of s is nothing but it is a closed loop system. The representation of a closed loop system has been formed by g of s divided by 1 plus g of s. And the error, once if the error has been generated in the signal, we have to identify which kind of errors based on the numbers. If it is a type 0, then it is a positional error. If it is a type 1, it is an acceleration error. Like that we have to identify the errors. So the finally we can able to identify the steady state error by substitution of limit. So steady state error equal to limit s tends to 0 s into f s. So normally the system is based on the time signal representation of time. So the time has been converted by step signals or in adding a system function by calculating the Laplace transformation. So here we are converting this time signal can be Laplace by limit s tends to 0 s into fs. So limit s tends to 0 s into r of s divided by 1 plus g of s. So the static error constants are figure of merit of the control systems. It is given by positional velocity, pressure, temperature, like. This means that it's a temperature control system. Positional represent the output temperature, velocity represent the rate of change of output temperature, and so on. So static error constant. The static error constant is it is a zero level indication because it doesn't have any additional signals over the system. So it can be represented by Kp limit extends to 0 z of s. So z of s equal to 0. So the automatically the steady state error is calculated by 1 plus Kp. The summary: type 0 system for step input equal to 1 by 1 plus k. For type 1 system it can be generated for only 1, so 1 by k. Type 2 system is generated for s square, like that, so it can be initiated by 1 by k. Assessment. How do you calculate the steady state error for step input signals? So normally we are going to calculate the steady state error for many kind of signals. So here the representation of steady state error for signals has been formed by step input signal a by 1 plus kp for a type 0 system. The first of all we may consider this will be a positional or velocity or acceleration system. So for step input signal it may be a type 0 system, so that we are going to calculate the positional error, and most probably it can be implemented based on the formulas. The general formula for this steady state error is limit s tends to 0 s into fs. So normally the equation has been calculated based on the input signals. So s into r of s divided by 1 minus gfs, like that. After considering this problem, we need to implement the constant error for this steady state. So while implementing the constant value, then automatically we can substitute the value of s equal to 0, so that we can get the final answer as s power 0 equal to 1, because it is a positional error. So it may be considered for type 0 system. Thank you.